Fun one. Jam-packed. I've been waiting to do this. I'm the last one, so I can finally pull it down from here and stop annoying the other instructors that have already done it. We get to do it today. I was in a chorus, and there was a 77-year-old, and he told me, yeah, I remember taking physics at the U, right in that lecture hall, right where you're sitting. And the only thing he could remember from the entire class that much later was this demonstration. So one, it's been around a long time. It's the biggest demo we have. I'm going to show you, hopefully. You can do the same thing with 2 index cards and an index card and 2 pennies. But that's not as memorable. So I'm going to start with this one, but before I do, any questions, concerns about things? Okay then, get your clickers out. While you're getting them out, I'll set this up and then explain what we're going to do and ask the question. Ankle's feeling better today, anyway. So here's our wooden bullet. We're going to load our cannon. And then we're going to take a monkey. I was happy. They had a little monkey and a softball, and they worked. But I saw this at a garage sale this past summer. Oh, this is perfect. So, we'll even. So there's an electromagnet over here that we'll hang him from. That's what the power supply is for over there. Try to get this from stopping swinging. Then we took that propane tank, and I'm going to fill it full of air. Good enough for now. So what we're going to do is we're going to try to shoot the monkey. Think of you're a hunter and you're aimed at the monkey hanging in the tree, but the monkey's smart, right? So the gun's aimed right at the monkey. When the bullet comes out, there's a little lever here. It's going to hit it. So as soon as it leaves the gun will apply a force and accelerate it up to a certain velocity. And it'll come out with that velocity. But then it's in the air. But it'll trip the electromagnet at the same time it's released. And so the monkey will begin to fall. Because he's smart. It's like he lets go of the branch in hopes that the bullet doesn't hit him. So that's our first question. Before we do it, I want to ask you what will happen. What do you think will happen? So the session ID number is down here. I'll go ahead and open polling. And what will this bullet do? Is it going to go above the monkey, hit the monkey, or go under the monkey? And then we'll do it and find out. So it's aimed right at him at first. But he's going to let go the exact same time the bullet's released out of the gun. See, we've got 20-some responses. Oh, look, he's scared. He's not even facing us. All right, has everybody had a chance to log in? It's quieted down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, most of you think it'll hit the monkey. Why do you think that? Because the bullet's falling at 9.8 meters per second squared. And the monkey? Okay, let's try it out. See if you're right. Oh, turn the lights up for this. All right. 1, 2, 3. Boom. Got him in the backside. So you're right. Very good. Knock the mask off of him. Let's go. He's good. So, chapter 10 on projectile motion isn't any different than anything else we've talked about. The only complicated part is instead of dealing with the two motions at the same time, we just think of them independently and merge them together in our brain, you know. So there's a horizontal component and a vertical component. We've dealt with both of those independently. So two-dimensional motion is really just two one-dimensional motions. And if we treat them independently, and I'm getting redundant, you can make sense of it. So here, yeah, they both fall at 9.8, so they're going to fall together. The only difference now is this has a horizontal velocity. So it's moving this way while it's falling. They still take the same time to fall, right? So it's like dunk, 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 and they hit. Does that make sense? Is the bullet accelerating? Yes, but in which direction? This way? This way. It's accelerating like this? Wrong. This is the combination. So break it up. Which way is it accelerating? Down. The only force acting on it is gravity, and that's down. So it's accelerating vertically. Horizontally, what's its motion doing? It's constant. It doesn't change. It stays at that horizontal velocity. Now this is neglecting air resistance, which is minimal in this case. Let's do it again, because why not? But we'll change things up slightly. So we'll reload. This time, we'll get somebody not quite as smart as a monkey. Sorry, BYU fans. This is the U, so you know. We'll give Cosmo a try. But this time, the ball has to go up. We'll see what happens. You know, while I'm loading and doing all this, let's see what you think for this one. I'll just ask you the same question. So polling's open. What do you think will happen this time? To me, the first one makes a lot more sense. And it seemed like most of you too, because it was aimed right at it. It starts out horizontal, so it's just going to fall. But this one, we're aiming it up. It's got to go up first. You know it's going to fall, but that can change things. It's going to have a different trajectory, different paths. Will it still hit? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh well, a few less of you think it'll hit it. But most of you do. More of you think it'll go above the monkey now. All right? Time for an experiment. Not 10. Force habit from the clickers. 3, 2, 1, 2. Yeah! Got him. All right, so somebody that got it right, tell us why it still works. Any takers? Oh, yeah.
Well, even though it's slightly different, they're the same horizontal plane.
Yeah, they're still in the same horizontal plane. Good, so it doesn't swing out this way. But why does it still hit it?
Gravity is the same.
The what's the same?
Gravity.
Gravity's still exactly the same. That's true. But this one has to go up, so it's going to take longer before it gets back down to the monkey, right?
But you increase the time on this side of the phone.
But the monkey starts higher. So it takes him longer to fall too. So it's still toom, 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 toom. This one gets decelerated, right? As it goes up, slows down, stops. Its velocity is 0, but its acceleration is still 9.8. Then it speeds back up this way. And so it's still being accelerated at a constant rate, just like the monkey. So remember this. If you aim at something up there, you know when you throw something, it curves. You know? You can get an idea where it'll curve by, if had it gone straight and started at that point and just fell, that's how far down it'll be by the time it gets over there. Because we just saw it. Does that make sense? So yeah, great example to show that two-dimensional motion is just two one-dimensional motions. All right. Let's do another one then. I think you'll get this. All right. Here's a spring-loaded gun. Just shoot something that way. I'm going to put one with a hole over here. And so the rod's going to come out from underneath through the hole. What will the block do? It'll drop. Its inertia keeps it in place. So, ready? It goes pretty much straight down. If I put another block on this side, it'll get pushed with a horizontal velocity and it'll look like this. So if we do them at the exact same time, what do you expect to happen? All right, this one's kind of hard to watch, so listen also. Because if we hear, then we know they hit at the same time. But if you hear, they didn't. You ready? The first hit was together. Did you catch it? We'll do it one more time once I find them. This came with spheres. They were a lot harder to find after they shot, so we made squares, blocks. Okay, you ready? Yeah, together. So these motions are independent. Did it fall off? Oh, here it is. Groovy. All right. So if you're in an airplane and you're dropping a bomb, how do you know when to release it? What do you have to consider? The time it takes, but in which direction? Do you wait till, okay, we're going. Oh, I'm right above the town. Let go. And it just falls. Does it fall straight? What happens if you jump out of a moving car? You always see them. That's because they have inertia. You're moving with the vehicle or the plane, or the bomb's moving with the plane, so they both have the same horizontal velocity, correct? So just because you let go of one, it just means now it's not going along with the plane anymore. It can fall. Gravity can take over. But it still has that horizontal velocity from before. So now it's moving that way, and it starts moving that way. So what's it going to do? The components of these, the result, it's going to go that way. Just like our bullet here, when we shot it up, some of this force on the bullet was up. Some of the force was over. Which way did the bullet go? in between these two. That was its trajectory. It had a vertical component and a horizontal component. So let's go along for a ride here and really convince you, drive this home. This little cart, I have a ball. It's a sad ball. I mean a happy ball. If I cock this gun, it's spring-loaded. When something goes past here, it trips and releases the ball, and it shoots straight up like this. So what happens if I move the cart, and right here it shoots the ball straight up? So when it gets here, it's going to release, and the ball is going to get shot straight up from the cart. What will happen? Well, you might as well attempt to get a point for this. Let you guess. This demo's... Oh, that was the on button. This demonstration is typically called the howitzer in the tunnel. So where will the ball land? In front of the cart, behind the cart, or in the cart? Again, the cart shoots the ball straight up. But I'm going to get it moving first, and it'll be in motion when it's shot up. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Get it in. All right, large majority think it'll land in the cart. Experiment time. Here goes. Close enough. You can see it traveled with the cart. It's time to retweak this a little. It's got to shoot perfectly straight up. Yeah, at least that one stayed in. They hit here every time. What if I go slower? Well, it still lands in. Again, because when it shoots, the ball now has an upward component, but it already had a horizontal because it was moving with the cart. So the resultant motion was the combination of these two, and it goes whoosh, this way. At the same horizontal speed the cart is. We're trying to eliminate friction here, and there's minimal air resistance on the ball. So as soon as it's released, horizontally, they move in sync because it's the same horizontal speed. Just meanwhile, this ball goes up, slows down, speeds back up, and lands back in. So going for the gusto, got to try it. Okay. Ready? All right! So yeah, next time you need to drop a bomb on something, or a care package, there you go. First aid relief. You got to plan ahead. The town's up there. You got to let go ahead of time. Because what's it going to do? It's going to have these two, and it's going to head off that way initially. It's going to, and you know how high up you are, so you could calculate how long it's going to take to fall. You know how to do that. Do you remember that one? That was that well. How far it needs to go, how long it's going to take. If you're dropping, that's gravity. Remember, you could count, you can spit off the San Francisco Bridge or drop a rock down into a well. If you know how long it takes, you know how far you are. If you know how high up you are, you'll know how long it'll take with this simple equation. And if that's how long it takes to fall vertically, you know how long it's going to take to go horizontally, don't you? How would it compare? That's right. I heard two answers that were correct. So yeah, you got this, you got this. So it heads off. like that. Think of this one. You went this way versus this way, but it took the same amount of time because they hit together. If your care package is going along, it's going to hit here at the same time. It doesn't like magically split in half. So the time it took to go horizontally from here to here is exactly the same time as it took to go vertically from here to here. To get down to the ground is the same time it took to get over. So they have to be the same time. That's what pilots do. They figure out the time from how far away they are, or how high up they are, how high up they are. And then they know how fast they're going. Or that distance is rate times time. Velocity is the change in position over time. So then they know how long to let it go based on their speed. When to drop it. Is this making sense? That didn't come out as clear as I liked, but you got it? You think their computer magically can do it for them? Well, it probably does. But you know the physics now to hit a target.
So when they drop the package, when the package hits in the middle of town or wherever, is the plane directly above?
What do you think?
Yeah.
Yeah. Where's the plane when this hits the ground? What speed does the package come out at horizontally? The same speed as the plane. So how far, if the package moves this far with that horizontal speed, how far does the plane move? Exactly the same. It'll be directly overhead because they had the same horizontal speed. Now this is assuming the plane doesn't veer off course or change its speed, which it can once it lets go of the package. But yeah, you just let go of it and maintain, you'll be exactly over it. Cool, huh? Let me do an animation. Where'd it go? Oh, there it is. Get the lights. Help you visualize this a little more. So here's an animation. If I turn gravity on, reset, this is just going to fall. It's going to take a snapshot of the ball every second, representative, equal time units, intervals. What do you think the pattern will look like for the ball? So it's just going to fall. If you took a snapshot of it every second, what will the pattern look like? The gaps will start getting bigger and bigger. Good, because it's accelerating. The speed is picking up. Do you remember? After 1 second, how fast is it going? Yeah, we'll round but 10 meters per second squared. Yeah. How fast is it going after the second? Well, what's the rate our velocity is changing at? The acceleration. 10 meters per second. 10 meters per second squared. So every second it's going to gain 10. So after 1 second it's going 10. After the second it's going 20. After the third it's going 40. So if it's going faster and faster every second, it's going to cover more and more distance. Vertically. All right, reset that. Let's turn gravity off. Turn the horizontal velocity. Now it's just going to get shot at a constant velocity horizontal. Oh, that way to you. What do you expect the pattern to look like? Equal gaps, good. It covers the same distance every second. That's our indicator that it's a constant velocity. Zero acceleration. Remember, it's in mechanical equilibrium. There's no net force on it. That's why it does that. So together, you just combine the two. And horizontally, it does the exact same thing it did before. And vertically, it does the exact same thing it did before. And instead of turning them both off, let's turn them both on. There we go. And it falls. So you can see, convince yourself here, horizontally, they're equally spaced. Can you still see that? Horizontally. But vertically, the spacing gets bigger and bigger each time. So here with sound effects. Horizontally. You can see it's the same. But it falls different. It falls less here, a little bit more there, a little bit more there, a little bit more there, a little bit more there. You get the idea. So let's do this one. This is this demonstration right here, where one's going to go horizontal at the same time one drops. They're in sync. This is like our slow motion video of this. Let's do it again. What if I shoot the red ball with less speed? What will happen? Will they still hit the ground together? Well, sure. It just won't be as far down range because it didn't have as big a horizontal velocity. But see, they're still in sync. Here's another way to look at this. When you shoot something, this is its velocity, where my arrow's at. The light blue arrow, if you can tell. So we break it into components. We're going to shoot something that way. So physicists like to think of it. Some of it's up, some of it's over. Neither of these are bigger than the original. You can see that in the vector notation. The magnitude is bigger for this arrow. But there's a vertical part of it and a horizontal part. Watch how they change as we shoot. This does it well, so I don't need to draw it. So focus on the horizontal one this time. The horizontal one. Is it changing? No, it's staying the same magnitude and in the same direction. Why is that? Why doesn't it change? Its velocity is constant, exactly. And why? Why does it stay constant? Why should it not change?
Well, there's no force acting.
Bingo. There's no force acting on it horizontally. It's in the air. We're ignoring air resistance. What would it do if there was air resistance? It would decrease. So watch it again. I don't have air resistance on this one. But it would just get a little shorter each time. A little shorter, little shorter, little shorter, little shorter. Due to the little bit of air resistance. Now focus on the vertical one. See, it decreases, decreases. The velocity is 0 right there. It switches directions and accelerates back down. Well, increases back down. It's accelerating down the whole time. Gravity's pulling it down, slowing it up, slowing, reversing direction, and speeding it back up. That one does change because we haven't got rid of gravity. So this one I can do in real life. Then I'll show you. I have a launcher over here, spring loaded. I'll put the ball in. Set it to 45 degrees. Okay, then I can release it. I bet you know where, you can guess where it's going to land. Not on my computer. So, I'm going to give it a velocity that way, but I want you to think in terms of vertical and horizontal components. When it's 45 degrees, which one's bigger? Horizontal or vertical? They're the same. Do you see that? The symmetry? Makes a nice square. So let's shoot that one. Yay! So, if I change it to 60 degrees, what's going to be different? What's going to happen? Good, I heard that. Yeah, so now instead of looking like this, it looks kind of like this. Right? This was 45. They're equal components. Now it's bigger up than it is over. So what's that going to do to the trajectory?
It's going to go
Yeah, it's going to go higher, but not as far down range. So I'll leave that there so we can compare. Let's pay attention to where it hits. You ready? Did you see it? On that former one, air resistance was not negligible. Okay. Boink. What was that? About here? Let's do it again for verification. Encore. Okay. So now let's switch to 30 degrees. Again, what's going to be different? Where's it going to land? Blah, blah, blah. Stop wiggling. Close enough for government work. I'll load it this time. I think I bumped it a little. Good enough. Okay, so 45, 60, and back to 45, 30. So yeah, it's going to go, it's more of the force is downrange, the velocity I should say. So it won't go as high, but it'll go further this way. Is that what you think? So it'll land further than past the bucket? You think it'll land in the same place? Why are you thinking that? You know?
Because it's the 369 triangle, doesn't matter. The angle is still the same.
Because 30 and 60 add up to 90. Let's just shoot it and then talk about it. Ready? Oh. Close enough. I guess we'll go this way. And again, for repeatability, am I still at 30? Close enough. So essentially the same distance. So those of you that thought it was further, can you reconcile this? So yeah, this one went up higher, not as far, as 45 degrees. But this one, let's start with 45. It's going to go faster horizontally than 45 does, yes? But it's not in the air as long because it doesn't go as high. So it doesn't have as much time to go downrange. Do you see? So there's a balance there. And there is this nifty rule. Very good. If the angles add up to 90 degrees, they land in the same spot. Any pair, they'll land in the same spot. A different pair might land in a different spot, but they'll be the same. That's my little animation here. And I do apologize. I know the big monkey shoot beams in some of your vision. Let's see here. So let's shoot 60 degrees here. Fire. Boink. And then if we switch it to 30, those add up to 90. It's going faster horizontally, but spends less time in the air. So they go the same distance because they add up to 90. If we do 75 degrees, will it go further or shorter? What do you think? A lot more time in the air, but there's a lot less horizontal velocity, so it'll go shorter. But 15 and 75 add up to 90, so at 15 degrees, lands where 75 did. And since we're here, let's end with 45. That goes the furthest without air resistance. Let's reset, turn on 60. This one, I can do air resistance and turn it on. Will it go as far? No. Will it go as high? Sorry. There's air resistance. Yeah, that slows it down a little bit each time. So, cool. Let's do this guy. There's a beautiful picture in your book. It's actually your author of the textbook that encouraged me to make this. This is what projectile motion does. We've already kind of discussed it. If you drop something from here, 1 second later, how far will it have fallen vertically? I asked you how fast it would be going. I don't need to write it. How fast will it be going 1 second later when you just drop something? Let's do this. This is a scale model. If I let go, how fast is it going after 1 second? 10 meters per second. Good. How far has it fallen in that amount of time? What's that?
About 5.
Very good. 5 meters using 10. Yeah. We could do this. This is the equation that does it. Let's see. 1 second, 1 squared is 1. 1 times 10 is 10, and half of 10 is 5. So it's gone 5 meters. Think of it another way. We did this before, but it was a while ago now. If it started out going how fast? 0. It ends up going how fast? 10. What's the average velocity in that first second? These are the instantaneous velocities, 0 and 10. What's the average throughout that 1 second trip? 5 meters per second. You add the 2 and divide by 2. 0 plus 10 is 10, divided by 2 is 5. So on average, the ball was going 5 meters per second. And if you go 5 meters in 1 second, see, it's 5 meters per second. That's why it falls 5 meters. So if this represents 5 meters, it's fallen maybe that far. Okay, how about during the second? What's its speed now? 20. Very good. 20. Let's do the average way first. Okay, what's the average velocity then for that second? How fast was it here? 10. How fast is it here? 20. So what's the average? 15. Yeah, in the middle. Add the 2 and divide them in half. 15. So it's as if it was going 15 meters a second. Well, this is a second, so it went 15 meters in this second. Are you with me? It's gone 15 meters in this second. How far did it go in this second? 5. Add those together, and it's now fallen 20 meters. That's why the spacing looked different. The first spacing was only 5 meters. The second spacing, whoosh, down here at 20. And so on. That's what happens. And it would look like this. So if you give something a horizontal velocity like this, do you see the trajectory would look kind of like these endpoints? It still falls exactly the same as if you dropped it from each individual point. It just moves over a constant distance horizontally because it has a constant velocity horizontally. So with that in mind, that's why the bullet and the monkey, right? The bullet's falling just like the monkey. And when you aim it up, tighter, come on. Good enough. So now the monkey's way up there, but after so long he's fallen this far. Well, so has the bullet. It's as if inertia kept it going. Turn gravity off and it just goes straight up the PVC pipe, right? But it falls the same distance and it'll land in these spots. So this little thing's nice. What if you shoot it higher? You can get the nice parabola here. This is like 75 degrees, 60 degrees, and so on and so forth. Any questions at this point? What's our time? 10 minutes? Hey, this is working out well. Well, then let me ask you some more questions with your clickers and see how you do. I always hit that button and don't mean to. Oh, while you're doing this one, I forgot to tell you, I messed up, and I apologize. Looked like it only affect one student who had only answered a few questions. Your next homework assignment, well, let's see, the one we're currently on, Chapter 7, is due Sunday night. But then we're on Chapter 10 now, and we'll do Chapter 35 on relativity Monday. Those are the next homework assignment. I didn't realize I made that available before I meant to this morning. I hadn't adjusted a few of the questions. Basically, I'm not asking you as many questions that were on there, and I hadn't removed them yet. I didn't mean for that to be available for you yet. It won't mess anything up. Is Philip here? He's the only student I noticed that started answering any, but it wasn't any with relativity yet, and that's the only things I was going to change. So I apologize if that messed anybody up. You probably hadn't looked at it yet, huh? Anyway, it'll be available shortly when I remove some of the relativity questions. I didn't mean to ask you as many as I did. So that's a good thing. So I apologize. You'll be able to see that after this homework assignment that you're currently working on. Okay. Looks like most of you have voted here. So a cannonball is fired horizontally at 10 meters per second from a cliff. Its speed oh yeah, I hope you get this one. We just did it. 1 second after being fired is about, there's just a little twist to this. It's fired horizontally at 10 meters per second. That means its horizontal velocity is 10. Then it goes off. What's its velocity? Or its speed, it says. Its speed 1 second later. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, most of you think it's 10. Some of you think it's 20. Okay, the correct answer is, drum roll, neither of those, it's 14. So what's happening, it's shot at 10 meters per second. If we just dropped it, what's its vertical speed 1 second later? 10. So after 1 second, it will be up to 10 meters per second vertically. What will its velocity be horizontally after a second? So it slows down? No, shooting now. Sorry. I apologize. In the shooting now, if you just drop it, yes, it'll be up to 10 meters per second vertically. If you shoot it, it'll still be 10 meters per second vertically. But what's its horizontal velocity a second later? What was it to start with? Is it accelerating? Is it decelerating? Is there any net force on it? So what should its velocity be a second later? 10. So a second later, it has 10 meters per second horizontally and 10 meters per second vertically. So it's gone like this. We shot it. Here it was all like this. 10 and 0 down. A second later, we're over here, and it's pointing this way. So it still has the 10 this way, but it now has 10 this way. Do you see that now? So the result is it's going to be more than 10. I didn't expect you to know exactly how much, but just from scale, that's going to be a square, right? If this is 10 and this is 10, what's the diagonal? Roughly 14. 20 would be too big. It's not twice as far. Had you guessed 16, I would have been happy too. But you sure this makes sense? So you can't forget about the 2. I'm very proud of most of you. You got the 10 vertically, but you forgot about the horizontal. All right, let's do another one. This one. Once you can see it. Yeah, maybe I'll show you my penny version next time. So your clue is this is kind of like this. You're going to have a horizontal, vertical, or perpendicular velocities going on here. Leveling off, so that means he's going 40 kilometers an hour. He levels off. He's not falling 40 this way. But there's a 30 now this way, a crosswind. So he levels off at 40, but there's a crosswind of 30. So relative to the ground, what's his speed? I'm helping you out. Before the crosswind, it is what? 40. Does the crosswind change anything? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 64% say C, and you're right. Good. You're going to have 30 this way and 40 this way. Well, 30 is relative to the ground. So is 40. So the result is that way. It's something a little bigger than 30 and 40. And it works out to be exactly 50. So had you done 60, I'm kind of happy too. But one more. Hopefully you'll get this one, and we'll end with it. We've done this one in class today. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh, good. Hey, yeah, if it's 45, then the up and the over are equal. All right, have a great weekend.